All right, so today what we're going to be looking at is harmonic motion. So really we got harmonic motion in two different scenarios typically. So the first one we look at is pretty much like if we have a pendulum as it swings back and forth, we say it has harmonic motion. And the other way that we have harmonic motion, if I'm just kind of talking about like in a classroom setting, is if I have an object on a spring. Actually, let's make the spring go up and down. And there's a mass that I just kind of suspend from the spring. When I let it go, it's going to drop down. And then the spring is going to pull it back up. And it's just kind of move back and forth in this direction. Just like a pendulum kind of just swings kind of back and forth along its arc. So with this harmonic motion stuff, there's a number of things that we could measure about it. For a pendulum, this part down here, the part that we have at the end of the pendulum, it could have a certain amount of mass. This string could have a certain length to it. One thing we do know is we could figure out, how much time does it take for one arc to be completed. Over here with the spring, we could look at the mass of the spring if we're talking, or that's attached to it. We've discussed earlier how all springs have a spring constant to them. And once again, we could also measure time, if you forgive my little stopwatch looking thing there. Okay. So there's a number of things that we can measure about these things. Also note, over here, with both of these, if we're doing them on Earth, you have something that's kind of hanging down, and even its arc, if I had drawn it better, it'd be a downward arc. I know that if I pulled this mass all the way up here, it's gravity that's going to accelerate it downward. So both of these are being affected by acceleration due to gravity. So then the question is, so out of all of these things we can measure, and I guess we could measure like the resting length of the spring and then the stretch length of the spring. There's a number of things that we can measure here. So the big question with harmonic motion is going to be, out of all these variables, which one's going to affect how long it takes? So for the pendulum, how long does it take for the pendulum to swing away and back? Or for the spring, how long in seconds does it take for that mass to bounce down and then come back up? So what that time is, we did a lab, we talked about how that was, one revolution essentially. We called that period. So the symbol for period is a capital letter T. No idea where that came from other than it is time, I guess. But it's a specific kind of time. So we know that it's period. And the unit for period is seconds. What's going to affect the period of a pendulum? From the lab you found out that it's equal to, we know that it's based on length was really the big determinant. The shorter the length, the shorter the period, the longer the length, the longer the period. But there were some things like when you graph out that data, just length and period, you're not going to get to a very, there's no clear-cut relationship there. You can't just get one to equal the other. So the rest of the equation we need to kind of make that work is 2 times pi times the square root of length divided by acceleration due to gravity. Keep in mind, if you're plugging this into your calculator and stuff, you're probably going to want to put that part in parentheses. Just to make sure your PEMDAS is right. And so the 2 pi part is pretty much just a constant. You can kind of think of it, if we're cutting out an arc, we're going to have some pi in there somewhere. And then the rest of it is just square root of length over acceleration due to gravity. What that means, though, is the higher the acceleration due to gravity is, the shorter your period's going to be. Or, if we vice versa, if we had this pendulum set up on the moon, the moon, the acceleration due to gravity on the moon is way less, so I'm dividing by a much smaller number. That's going to allow my period to be longer. The pendulum's going to take a lot longer to swing back and forth than if I was on like Jupiter or something. So that's the formula we use for to figure out period. So L is length, and that'll be in meters. And acceleration due to gravity is in meters per second squared. You know, if we're on Earth, it's just 9.81. Now, if I was sitting kind of underneath this pendulum, really, I'm not going to see the thing move in an arc. I'm just going to see this object move back and forth. You know, if I'm laying underneath the pendulum looking straight up. And it's going to look just like how this mass on the spring is moving. Essentially, it's just going to look like the mass is just going back and forth. This block on the spring is just going to move up and down. So those two periods are going to look very similar. And in fact, we might even say that this is period. We could add a P there so we know it's a pendulum. The period for a spring is going to look a lot similar. You know, if I'm going to calculate this out, it's 2 pi times the square root of the mass of the object divided by the spring constant. And once again, if you want to put that there just so you remember to put that in for the calculator for your order of operations, that's probably not a bad idea. So really, we still got the same constant, this 2 pi. We still have a square root of essentially some ratio. In this case, it's just the mass of the object over the spring constant. So the formula is really straightforward. So for instance, we look at number 1 there. You need to know the height of a tower, but darkness obscures the ceiling. You note that a pendulum extending from the ceiling almost touches the floor and that its period is 12 seconds. How tall is the tower? All right, so right now, we can assume we're on Earth, which may be important. It probably is. We know we're working with a pendulum, so right off the bat, I know that I'm going to be working with this equation right here. And they tell us that the period is 12 seconds. All right. They want to know how tall the tower is. So if I'm kind of thinking like, let's assume this isn't the Leaning Tower of Pisa. All right, tower, essentially there's no floors in the tower, and there's a pendulum that's kind of set up, and it just kind of swings back and forth. And you're able to see that it takes 12 seconds for it to do so. Essentially what we're going to assume is that the length of the pendulum is the height of the tower. So we can begin by just plugging in what we know. So we've got 12 seconds. So we're using a pendulum. They gave us a period for it, so we're using this equation here. 12 seconds is equal to 2 times pi times square root of L over AG, acceleration due to gravity on Earth, once again. That is 9.81 meters per second squared. So then the question is, shouldn't it be negative? You can do that. Essentially, that means your L is negative is 2, since we talked about it decreasing in height. I would say leave it positive, just so that way we don't have to worry about like taking the square root of a negative anywhere in there. It's my way of glossing over that math. So really, the first thing, I'm going to try to get L by itself before I do any math. So the first thing I'm going to do is divide both sides by 2 pi. So I'm going to have 12 seconds divided by 2 pi is equal to the square root of L over 9.81. I could do, split this up into the square root of L over the square root of 9.81. What I'm probably just going to do is I'm just going to square both sides first. So let's go ahead. That's in parentheses. That's in parentheses. Let's square both sides. So now I'm going to have 12 seconds over 2 pi squared is equal to L over 9.81 meters per second squared. Forgot that unit there. So now to get L by itself, I can multiply both sides by 9.81. So I'll have 9.81 meters per second squared times it by 12 seconds over 2 pi all of that squared equals L. All right, so my math's all set up. What I'm going to do, I can do some quick unit analysis as well. So length, we already know length should be measured in meters here. Well, I've got 12 seconds in the parentheses here, but I'm going to square it. So I'm going to end up with seconds squared here, and that's on top. Down here with my 9.81, I've got seconds squared on the bottom. So that means my seconds squareds will cancel, leaving me with just meters. Okay, just go through some quick, what's the word I'm looking for? Unit analysis, my bad. All right, so let's go ahead and bring up the calculator. And let's see if I can do this, plug this in right. All right, so I've got, let's take care of that parentheses part first. Let's go 12 divided by parentheses 2 pi, close parentheses. Did I forget the 2? Let's start over. Let's just go 12 divided by 12 divided by parentheses 2 times, I forgot the times, that's what I forgot. Close parentheses equals, we're going to do this piece by piece. Let's call that 1.9099. All right, so I've got 9.81 meters per second squared. And I need to square that number still, so let's go ahead and just square that. 1 point, okay, let's just do this. 1.9099. Why is that not squaring? All right, so my calculator said exponent. That's what I want. 1.09099. Nope, that's not what I want. .19. All right, good enough. Thank you, Flipboard. 1 point. Wow, technical difficulties today. 1.19, and right away we already knew that was seconds squared. Second squared, second squared. So 9.81 times 1.19 times 9.81. Keep in mind I'm not doing sig figs or anything like that. Let's call that 11.68. All right, and that's meters. All right, so that's just the length of the pendulum. Sorry about the calculator mishaps there. So that's the length of it. One last thing I do want to talk about, since we are talking about harmonic motion. Period is how long it takes for one revolution to occur. So let's even go, let's fix this quick. So period is how long for one revolution. When we're talking about waves, harmonic motion, typically we don't talk in periods so much. What we do is we talk about frequency. And in terms of harmonic motion, frequency is the number of revolutions, and I'm going to say per second. And really the difference between them, so the period is how long it takes for one revolution. The frequency is how many revolutions do we have each second. And so to convert between the two, you just take, or you just take 1 over period to get frequency, or 1 over frequency to get period. Typically, once again, period is measured in seconds. For frequency, we can either do like revolutions per second. Typically, what you're going to find is that it's measured in hertz, which means the same thing. It's just how many revolutions per second do we get there. When we move into waves, wow, this video is getting long. We're going to be talking about how long does it take for one wave to pass a point, or how many waves there are each second. Really the same thing. All right, good luck.